not believe it, but I have never studied English at school. Today I have been asked if I could run this lecture in English for some reason, so I try. Norwegian, in fact, is easier for me since I have been more or less in Norway for 24 years. But I have never, again, studied English at school. And why do I tell it? Because I think that if you are motivated to do something, you can do, even if you have not received formal education in something. In fact, at school, you now will think that I am a kind of ancient, middle-aged character. At school, I studied ancient Greek, Latin, and German. German, at least, it was useful because when I came to Norway, I could learn Norwegian very quickly. But anyway, this lecture will be in English, and if you have any question, you can ask either in English or in Norwegian or in ancient Greek, of course, or Latin or Italian. And afterwards, I will ask you, how it works to have the lecture in English compared to Norwegian. This lecture will be only 1 hour, so you have time at 1 o'clock. Those of you who have to finish your exercise 2, you can go to the lab or wherever to finish your exercise. There are 4 topics we cover today. We cover chapter 7, but concerning the case study about the weather station, I cover it in a slightly different way than the book. I think I cover it better than the book does. And for those of you, I think everybody who is interested in the exam, so I really encourage you to understand this case study about the weather system very well, because if you understand it, so you have come very, very far with respect to the exam, with respect to the project. So try to follow, try to write down things, try to see relationship between the different diagrams, because this will be some important part for the exam. Yes? I thought it was on, but we... Is it better now? Yes. Now, where are we? Yes, we have 4 topics. The first one is this case study, and the case study is in chapter 7, but what's happening now? But as I have promised you from the first lecture, while chapter 1 introduced 3 case studies like this, I have tried to go in depth in each case study. The first one about this mental health information system, the second one about insulin, and today we are going to see the case study about weather station, and this case study is very well suited when it comes to low-level design and implementation and state diagram and interface declaration. So it's very good to discuss this case study when we look at design and implementation. And again, be sure that you understand it very well, because if you understand it, you are come 30% already in having a good knowledge for your exam. So we will have an extra pattern. Last time we saw 5 patterns. Let's say, if I remember them by heart, we saw model view controller, layered architecture, we saw pipe and filter, repository architecture, and client-server patterns. Today we are going to see another pattern, and you may answer, but why do we look at this pattern today and not last day when we talked about architectural design? It is because the design pattern observer is something that you take into use when you deal with low-level design, while the patterns we saw last time are patterns that have with not functional requirement to do, so they are patterns you take into use when you deal with architecture. If this distinction is still strange, please reflect on it, please try to understand why do we look at the observer pattern today and not on Thursday. Because today we are looking into low-level design issue, and the observer pattern is something that is useful when we go and take decision at low-level design level, while the patterns we saw last week, no, this week, but at the beginning of this week, there are patterns that are important when we make architectural description. So we have a couple of slides about implementation issues. With respect of the book, I try to give examples that are more relevant, more modern somehow of those in the book. And in the end, we talk about open source. That is something I hope I talk a bit about each day, because I think it's a big responsibility we have here to make you aware, to make you knowledgeable about issues in open source. Okay, so it becomes to be a bit boring for you, because each time I come here and I show software specification, software development, software validation, and software evolution. And each time I ask you, where are we now? Now we are here, we are at a bit lower in the software development phase. We are attacking a phase that comes after architecture design, and that is low-level design and implementation. Next week, it will be the testing week. We will have 3 guests coming here and talking about test. I will give a lecture about test, and you will have your exercise about test. So look forward to the testing weeks. That will be this software validation phase that is the next phase after software development. So the case study, we are going to look at this weather station case study. The book has a lot of words about this. I have Googled a picture about why? I am a weather station myself. What's happening? Maybe it's this mafia accent anyway, a weather station is something that looks like this. Is a combination of sensors and software, and it has a display that can look like this, that can show the temperature, can show the humidity, can show the wind forces in the places that I want to inspect. And yeah, I don't think I need to say more. You see how a weather station look like. And this display, that is quite important to think about and to imagine today while we attack the observer. Why? Maybe it's kan det være noe som jeg har på? Okay. Okay, no, because it was really annoying. Okay, today that we are going to look into the observer pattern, it's good to have in mind something like this that we are all used with. We are going to talk about how to implement systems like this. So I will not read every word of this description, because this is in the book, because you can read it yourself, because you can imagine how a system like this may look like. Somebody wants to have control over temperature and generally climate issue in remote places, so we mount several of these weather station system, and we want to have a central system that is able to receive information, is able to send updates, is able to send control information. So in this example, try to focus on the fact that some of these descriptions in English are more formal than other. Here is a quite informal, high-level description. Here we are not at design level. Here we are at requirement specification level. The government of a country with large areas of wilderness decide to deploy several hundred weather stations in remote areas. Weather stations collect data from a set of instruments that measure temperature, pressure, sunshine, rainfall, wind, speed, and direction. The station includes a number of instruments. We saw this device with all its interests, and each interest is controlled by a software system. This is what we are going to look in detail, that takes parameters, readings periodically and manage the data from the instrument. This periodically is a word that I invite you to reflect upon, because we will, when we will go and design and implement our system, we will design and we will specify how this word periodically is implemented in a software design. Many of you know already how to translate something like periodically in a low-level design document, but those who don't know, please follow up, and I will try to show you how we map this periodically into something more formally. Additionally, software functionality, the system has to deal with power and communication. The system has to deal with, communicate with generator, and it has to support dynamic reconfiguration. When we will go and look into the state diagram of the system, you will find this information that now is expressed in English at a high level. You will see how we can map it technically on a state diagram on the methods of the classes. Okay, another description that is slightly more technical. This is something that could appear at the level that could appear in an exam, or at the level that appears in your common project. Is a kind of software specification that is in English still, but it's more precise than the one we had before. If you don't know what an anemometer is, I did not know either. I had to remind myself. Is something that measures wind force. Barometer, maybe you know, it's something that measures pressure, and rain gauge, okay, is something that measures the quantity of rain. Okay, so the first issue that the book introduces about detailed design is system context. The first thing we have to do is to decide our system, which boundaries, which communication it has to the external world, and understanding the relationship between the software that is being designed and its external environment. And this must be understood both at a static level and at a dynamic level. And it is not new for us, because from the first lecture we have been looking at class diagram, which display static information, and we have been looking at use cases that at high level display the interaction between a system and its actor. So it's exactly the same kind of diagram, but that now we use to model the interaction between our system, this weather station, and the systems that surrounds it. So it's the same exact syntax that we have been dealing with for many weeks now. We have our weather station, this one, that is the topic of our specification, the topic of our low-level design. And we see, okay, in the specification, they say that there will be a satellite that is connected to our system. So we model a satellite system. There is a control system, and there is a more general weather information system, which has the objective to collect the data from all these wilderness stations to carry out some data processing and to analyze and archive the data that comes from this weather station. So this is a diagrammatic description, is a class diagram that shows the context, the system context of weather system that is the topic of our case study. So it's this weather system that is our focus, but we look at the other system for the reason that we want to put it into a more general context. Concerning the interaction model, as I told you, we model the interaction between the weather system and the rest of the system by means of several use cases. And please notice that the actors in the use cases are not humans, but they are systems themselves. This is something that is allowed in UML, it's something that I told you when I was teaching about UML the first day. Actors can either be roles, persons, or they can be other systems. So if during the exam you get a question, model the dynamic, model the context of the system from a dynamic perspective, please specify a use case in which you specify the other systems as actors, and you decompose the behavior of the system into a high-level use cases. And in this case, we have report weather, report status, restart, shutdown, reconfigure, power save, and remote control. These are the functions that our weather station have to implement and that we have specified in informal English in the first slide of the presentation, and that are described in the book. So when you will come and start to prepare for the exam, don't look for 12 examples. Study a couple of examples really well. Try to understand this example very well. Try to understand this health patient system very well. And try to understand the examples that I made during the summer for the previous exam. It will be enough to have a good understanding of this part of the course, but try to understand it really well. So we take one of the use case, we take this report weather, and we can decompose it further into a textual use case. Those of you that have done your first exercise have already have already made a textual use case, and you see that the textual use case, as you know now as well as me, is something that has a title, actors, a formal description, an input, a stimulus, a response, and some additional comment about its behavior. In particular, this report weather is a use case that sends a summary of the weather data to the main information system, and this data that are sent back, of course, will be a summary of this we have learned now, is a summary of temperature data, barometric data, wind data, humidity, and so on. And the wind direction as sampled at 5 minutes interval. Nobody told us that it should be 5 minutes, they told us that it should be periodically, but at this level somebody has made a precise choice that periodically means 5 minutes. So we go ahead and we see the high-level architecture of the weather station. Again, this in principle doesn't belong to this lecture, because this lecture is about low-level design. This is architectural design, but in order to comprehend the low-level design, you understand that we must comprehend the decision that has been made at architectural level. So we see there that the architecture is a traditional client-server architecture. We have 6 modules, 6 components. One is dealing with power management, one is dealing with a different instrument, data collection, configuration manager of the weather station, fault manager, and communication to the satellite. we go inside one of these components. This is very typical for the components that are most important. We ask for further specification. We go inside the data collection, and here we have a pipe and filter pattern that describes how this component is constructed, and this is constructed very simply by three pipes, the one being a receiver, the second being the main weather data process, and the third one being a transmitter. So again, we have a client-server architecture, and when we go inside this client-server, one of the components is worth further specification, and we specify it with a pipe and filter pattern. We go ahead, now the architecture is in place, now we have to start the real detailed design, and we have to do something that you have been doing during your exercise this week. We have to identify the classes, the method, and the interaction between the different classes. So the book tells us about a bit of theory about how to derive classes in a formal way. You have been doing by using your intelligence and your common sense and the discussion between us, and this is what people mostly do in the real world, but there are methods to derive classes and objects in formal way. There are courses that we offer at ED that are advanced modeling courses where you learn a lot about how you can derive classes and objects and association in a formal way. The books list these 4 ways of deriving classes and objects. I am not expecting that you become proficient in these 4 ways of deriving classes and objects. I expect that I can ask questions like comprehension question about these methods, but not that you have real practice in all these methods, because we don't have time in this course. But what is nice in this weather station example, that we will have a practical application of point 2. In this weather station example, we derive classes and relationship by looking at the physical objects in our system. Because here it's easy somehow, we have this physical weather station, we have physical wind sensor, we have rain, we have temperature, but it's not always the case that we have physical objects that help us to derive classes and associations. So we have these 4 possible ways. At your level, it's very good if you manage to derive reasonable classes and association by using your common sense and discussion between us. So as I told you, the classes will be the object, the physical object that I find in the description of the system. So it will be something called weather station, of course. It will be something called weather data, ground thermometer, barometer, anemometer, all these physical things that we are dealing with, all these things that in fact at the beginning we saw in this display that are displayed will be the classes in this example. And I can expect that if in the exam there will be something like this that is very based on physical object, that it will be good if you go and find classes and objects in a way that resemble this exam. Use your intelligence, use your common sense. If you get a case study that is similar to this, try to be inspired by this. If you get a case study that is similar to the patient information system, try to copy, to be inspired by the other one. So here we have our classes, and here I ask you to copy down on a piece of paper. Don't copy my handwriting, that is bad. Copy what is written that. I want you to write down the weather station description, both name, identifier, and methods, because we will use this in the next slide, trying to put things into context. So we have a method called report weather. We have a method called report status. We have a method called power save remote control and reconfigure and restart and shut down. I want to go a bit further in order to understand what it comes afterwards and see what these methods will return. The methods report weather will return a weather summary complete. The method report status will return a test status. The method power save will not return anything. The method remote control will not return anything important. The method reconfigure will return something called configuration done. The method restart and shutdown will not return anything. So please write down these things, and so we will go ahead and try to understand how things go together when we come to further low-level design. Okay, sequence diagram. We have been studying how to define a sequence diagram since lesson 1. Yesterday I talked to one of the assistants. He showed me some of the examples you are doing, and people is doing well, making simple and effective sequence diagram. The sequence diagram showing the data collection part of this weather station can look like this. We have 5 objects, the first one being the weather information system, the external system, and the other one being an object of type satellite communication, an object of type weather station, an instance of the object we have been writing on the blackboard, an object called communication link, and an object of instance weather data. And here you see it's not so strange that when the weather information system issue a request to the satellite communication, so the satellite communication issue a call report weather to our weather station, and the report weather you saw up there is exactly this method here. This is not something mystical. It's the sequence diagram has to show how the objects interact with each other, and you know now better than me that each object interacts by means of its method, of the interface it has. So looking at this class, when I have a sequence diagram that have with this object of this class to do, I must use the same method that I list here in the interaction with other objects. If not, there is an inconsistency between the different models. Now we don't have neither the time nor the space to have all the classes and all the methods, but when you will go in depth in this example, you can make an exercise, and for example, for weather data, you write down all the method of weather data, and you will see that this summarize is a method of that class. You have to do this exercise and try to put things together as we do now with the single class. We come to the state diagram of that class, and of course we do not need state diagrams for all classes, but for a class like this, which has a complicated and important behavior, we have to go and specify the behavior by a sequence, a state diagram. And here it's important that we go and see, okay, here I have a shutdown. It's the same shutdown that I see here. What does it mean? That when somebody issues a shutdown to the weather system, the system has to go into a state that it is shut it down, and to get it up again, I will have to issue a restart that is the same restart that I have here. For each transition, I can do this exercise and say, okay, when I am in a running state, what can happen? It can come a remote control command from the central information system, and so I will go in a state that I am controlled by the remote central information system. Okay, I see this remote control is here. To come out from that state, there will be some other action that we don't specify here. When I am in a running status, it can come a report status method, that is this one, and this method in the end, when it is ready, has to return something that is called test status. No, test complete, sorry. You should follow up when I do mistakes like this. Reconfigure, that is something that is here. This is a bit tricky, because in order to go from shutdown state into a configuring state, I need two messages, not only reconfigure, but also power safe. This is a way, this is a choice. So I go into a configuring status, and when the configuration is done, I come back into running. I think that you can just play with this state diagram yourself, trying to map this into this, and trying, if you need to go back and look at the explanation we had about state diagram in the first lecture about UML, when we saw this Owen, this specification of the micro Owen. Now we go ahead. Here we have the interfaces of two other classes. When we ask to specify interfaces, you can either use Java if you prefer, or you can use the UML notation. It's exactly the same. Okay, so now this case study is finished. It's the third of the 3 case studies that I want you to really go in depth and understand. We look at the design pattern observer, that is a solution at micro level for implementing systems, part of systems like this, that have to display information according to different visual paradigm. I haven't talked to Doug Svanes yet. I assume about this, I talk to him very often, but not about this. I assume you go through the observer pattern in the MME course too, but I am not so, I don't know exactly yet. How do you specify the pattern? You specify with the same syntax we saw last time. And the pattern observer is a pattern to separate the display of object state from the object itself. All the languages, the object-oriented languages, provide a way of implementing this observer pattern so that you don't have to implement it yourself, but you have to understand, I have already told you about this, you have to understand that an observer pattern is something like this. You have a subject. In our case, it is this weather data. And this subject is observed by different classes that will display the status of the subject in different ways. For example, observer 1 display with a pie chart, while the observer 2 display with a bar chart. This is something that when you have understood, in the programming language that you will go and implement, you will be able to reuse this graphic representation and apply them. How does the UML of the observer pattern look like? I have the class subject and observer that will be offered by the language, for example by Java, and you will have to specify concrete subject and concrete observer. This relationship here is an inheritance relationship that we say concrete subject is a subject, concrete observer is an observer, subject consists of. This way of having this black ball is something that if we want, we can, I prefer this notation to write 1 to n. And a subject will consist of one or several observers. So this, I think, I am confident that this knowledge is in place because I know that you have been doing this exercise and the exercise looks good. So we don't use more time on this. And we can go on implementation issues. And here it's tricky again, because when people talk about software engineering, they expect that software engineering is about programming. Software engineering is also about programming, but as we have understood, that is about everything that is around programming. And important issues in software engineering are reuse, and these patterns are a way of achieving reuse. They are configuration management, that is a topic that we will look at the week after the testing week, and testing, that we will really go in depth next week. The development, the book has some pages about development tools and development platforms, and I encourage you to read them to know the theory back tools and platform. In practice, what we mean in year 2013 when we talk about tools and platform, we mean tools like JUnit for testing. We mean Cobertura for coverage of testing, Findbugs, Git. I know that soon you will have to start your project. You will have to choose whether to use SVN or to use Git or to use another system for version control. These are the typical implementation issues that are important at software engineering level. It's not only important that we make a program that functions, it's important that we have a reflected relation with respect of all these tools. Like for example, the building of the system. Are we going to build to use Ant? How are we going to build and rebuild a configuration of our system? This is something that each group will have to choose together with the group and together with the assistant. And of course, if you have a question for me, I will try to help you as much as I can. And of course, many of you are already proficient in Eclipse, and those who are not, I encourage you to use time to understand Eclipse, that is becoming a standard in Java development and provides support for most of these tools that are important to know about when we deal with software engineering. So, implementation issue, it was very quick. Please talk about these tools. Go and look at the home pages of the tools if you don't know about them. For example, for Git, it's very, in my time, configuration management was really very low level and very, very technical. I was very positively surprised. Now I have opened an account on Git, and it's like opening an account on Facebook, and it's really, you get examples and a very nice and simple way of learning configuration management. So I'm sure that if you use a half hour in front of the Git web page, you learn a lot, and you can get a lot of inspiration. Open source system. This is something that is very near to my heart, not only to my head. I have been working with Linux since the 90s. I have been working a lot with systems like Arduino, processing, GIMP, Scratch, that are systems at the intersection between software development and more creative expression. We have this MySQL database that in fact is partly developed here in this town, and we will get a person coming here and telling about the database and the software engineering issue in the system. We have Java that you have already been using. Apache Web Server is a system that is used on more than 50% of all web servers in the world, that are many million. So imagine that something like Apache, which is an open source system, is so much in use. People know more about Linux than about Apache, but be aware that Apache is really big and is somebody that everybody is using all the time, because we are all the time on the web, and the requests we are making are going through a lot of Apache web servers. So open source development. Open source development is something that has its root. I could talk about open source for many hours, but I don't do it now. It's something that has its root in free source, and that is something that started before open source, the Software Foundation. And when I say 1989, I mean it was the time when this Free Software Foundation rules and website and things were established. And yeah, what I want to say there, that it's important when open source is something that it's important to distinguish between having the source as open and the process as open. Open source is not something binary that you say either is closed or is open. It's much more complicated. In principle, in order to be able of talking about open source, we must have something which have the code that is freely to be inspected by anyone. Otherwise, we cannot talk about open source. Being gratis doesn't mean to be open source. Freeware is not open source, because the fact that I can acquire a program gratis doesn't mean that the program is open source. In order to be open source, I must have access to the source of the program. But having access to the source of the program doesn't mean that I can automatically become a developer in that project. For some projects, like for example the Linux project, it is true that everybody can in principle contribute with new code. For projects like Scratch, in which I have worked many years, it is not the case. Scratch is released open source by MIT, but if we find bugs, whatever in Scratch, they are not interested in committing our changes back into Scratch. So there is a level of having a source code that is open, there is a level of having the process that is open. In between, there are several levels, because many users don't contribute, in fact, with code. They contribute with documentation, they contribute with translation, they contribute with error descriptions, and so on. So the important questions that I meet a lot of ignorance in my life around open source, because the question are, should the project that is being developed make use of open source component? And this is a question that we should always ask ourselves and not be religious about that. I want to use open source, or I don't want to use open source. I should always ask this question: is it possible to use open source tools? And for example, in my case, as a teacher here at NTNU, if it's possible, I want to use. And so, should an open source approach be used for the software development? These are two different questions. Do I want to reuse open source components that others have done? is one question. And what do I want to do with my project? This is something that I ask to my master students, because you, as student at NTNU, you are the owner of your software. So in principle, it's you who decide what to do with the software you make. So I encourage my students to have an open approach to the software and make it open so that other students and other people can build on top of it. But this is a choice that you, as students who produce software, will have to ask yourself and you have to be aware of. Another question that the book is very is a bit simplistic about open source when it says more and more product companies are using open source as an approach to development. We have been doing a lot of research about that and we don't have conclusions. We are not sure if this first sentence is really true. It's true for systems like Google, because we know that Google is trying to give everything out as open source. Is true for new kind of development like Facebook, that we all know is based on the LAMP open source stack, but it's not so true for systems in the traditional sectors like oil sector, like the public administration. We see that this Altin, for example, that we have been talking about several times, is something that is not open source. So it's a complicated and an open topic. And the fundamental principle of open source development is that source code should be freely available, and this is this point here, but it doesn't mean that you, as the one who have made the software, is not the author of the software. Open source philosophy is clear about authorship. You are still the author, and you, as the author, can decide which license you want your software to be available. And when you decide the license, you will choose, there are dozens of licenses, but in my mind it's important to have understood these three levels. You can choose the GPL, that is the one that is most near to the free software philosophy, that say, okay, this software you can reuse, but each software you make on top of this will also be open source. That's why GPL is called viral, because GPL says if you use this, okay, please use it, but what you do will have to be GPL. So you have the less GPL that say, okay, you can write component that link to open source without having to publish the source of this component. So it's less restrictive. The third one that is very that is more open, that is called Berkeley Standard Distribution, BSD, that is very similar to the license that has been adopted and remade by Apache. It says not only you can build on top of my software, but if you want, you can even make it as a commercial closed source software. So it's important that you understand these three licenses, because it's a responsibility I think we have here is to educate people about open source. I think it's both a responsibility, but also it's a very smart choice to do, to participate in one or several open source projects, because it's something that is good for your CV when you will go and apply for a job. Of course, you will be a Master of Technology from NTNU or a Master of Science from NTNU, but you will also have some open source project you have participated with in your career, and it doesn't mean that you have to code. You can at the beginning help with translation, you can help with bug report or whatever. And this license is also, again, very important. Be aware that there are a lot of licenses, and be aware that there are at least these three levels of licenses in open source that make the picture more nuanced than being either closed or open. Okay, thank you.